that we could talk about them almost forever. So let me share with you some of the really interesting and important relationships that we can actually use to solve real questions that have come up in real math life. The first one comes under the heading of the chord-chord product theorem, which basically says if we have two chords that intersect somewhere inside the circle, then we notice that we have four segments, this line segment, this line segment, this line segment, and this line segment. And what this basically tells us, this theorem, is that if we take the length of AE and multiply it by the length of EB, then what we get is the same thing as taking the length of CE and multiplying it by the length of ED. So basically, visually, if you have two chords that cross inside the circle, this length times that length will equal this length times that length. Again, a beautiful property due to the beauty of the symmetry of the circle. So here's an example. Here we have a circle. We've got two chords crossing. We're told this is 2, this is 3, this is 12, and we don't know what this is. And so our job is to find x, and then find the length of each of the chords. So how would we find x? Well, I know that since they're crossing like this, by the chord product theorem, I have at my disposal the fact that this times this equals this times this. So that means that 3 times x, or 3x, will equal 2 times 12, which is 24. And so if I solve this for x, I just divide both sides by 3, and I see x equals 8. That means that this is 8 right here. What are the length of the chords? Well, this chord's actually pretty easy to find out. This is just 12 plus 2, so that's 14. So we have that BD equals 14. And what's AC? It's going to be 8 plus 11, which is 19. So you can see that this great chord product theorem. Now let's see, let's just make sure everyone's happy with everything in life. So let's see. If we take the 12 and add the 2, we get a 14. If we take a 3 and add 8, how do we get 19 again? Can you remind me of that? I don't actually remember that. So let's think about that carefully. If this is 8 and this is 3, then the whole thing is 11. So really, I meant to write 11. So AC has a length of 11. So you got it, because this is 3 plus 8. Those of you who think that 3 plus 8 equals 19, you're in my camp of math, which is not a good camp. So let's get into the 8 plus 3 equals 11. Cool. All right, let's take a look at a real-world application question that one day we might be faced in our everyday lives. Imagine that we have a perfectly round pond. And inside the pond, there are little things growing, and there's a little duck swimming around. And then we're given these two chords. One chord is the red chord, called PR. The other chord is the blue chord, called SQ. Now, we're told a whole bunch of things about these things. For example, we know that PR is the perpendicular, or is a perpendicular bisector to SQ. That means that not only do we have a right angle here, but this length actually is going to equal this length. And so automatically, for free, I know that this length right here is 10 feet. Okay, now what's the question? The question is to figure out what is the length of PR. I want to find out that whole length. Well, how can I do that? Well, one way to do that is to notice that I can think of these as two chords that are crossing inside the pond. And so therefore, I can find this little piece. If I call that thing, maybe I call that thing D for duck. Then I know that 5 times duck will equal 10 times 10. That's what the chord result tells us. And so I see that 5 duck equals 100. And so therefore, the duck equals 20 feet. So this length right here is 20 feet. What was the question we were asked? The question we were asked is to find the length of PR. So the answer is not 20. The answer is this whole length, which is 20 plus 5, which is 25. So the answer is 25 feet. And you can see how we did that using the chord result. Very cool, very cool. Nice application, nice duck, nice theorem.